Welcome you all. Today we will discuss about minimum spanning tree, algorithms and applications. So here is the outline of the discussion. First of all, we will discuss about introduction to the minimum spanning tree. Here we will discuss about spanning tree, the definition of the spanning tree, minimum spanning tree, and the difference between minimum spanning tree and the shortest path. Then we will go for the historical background of the minimum spanning tree. Here we will discuss about Boruka's minimum spanning tree algorithm. So we will discuss the problem definition, basic properties of the spanning tree, and Boruka's algorithm and other approaches. Then we will discuss about various algorithms for finding minimum spanning tree such as Prim's algorithm and Kruskal algorithm. Then we will go for the applications in which minimum spanning tree concept can be used. We will discuss and we will go for the exercise, take home exercise and the references. So we'll start with the introduction to the minimum spanning tree. So before proceeding to the minimum spanning tree, we'll discuss about the spanning tree. So the definition of the spanning tree is a tree which selects an edge such that each vertex is connected to other vertices, and we have to select the number of edges in such a way that the total number of edges that are to be selected are less. For example, if you consider a graph shown in the figure 1, a graph is having 10 vertices, v is equals to 10, and number of edges that are available are e is equals to 21, where v is a set of all the vertices and e is the set of number of possible edges. So we will find out the spanning tree from this figure 1. So one of the possible spanning tree is shown in the figure 2. So as we can see, we have selected 9 number of edges that are connecting all the vertices. So there are a number of spanning trees that can be possible. So it is one of the possible spanning tree for the given graph shown in the figure 1. So important point here is that if there is a loop that is being found, so we can omit one edge. It means that the one of the edge is not necessary in that case. Now we'll go for the minimum spanning tree. So definition of the minimum spanning tree will be a tree which selects an edge such that it will be a spanning tree and the sum of weights on the edges is as small as possible. So from the definition we are having one more new concept of weights here. So weights are assigned on the edges, so the sum of weights on the edges that we are going to select as a spanning tree is as small as possible. So the mathematical definition of the spanning tree is, given an undirected graph g equals to v comma e, where v is set of vertices and e is the set of edges, find the minimum weight spanning tree where wij represents weight on the edge ij that is belonging to e is also given. So the weight on the edges that are available in the graph is also given by e. For example, we will consider the same graph as shown in the figure 1, but now we will assign some weights on the edges. For example, we have assigned the weight on the edge from A to B as 10. As it is an undirected graph, it means that the weight from B to A is also equal to 10. Similarly, we have assigned a weight from F to G equals to 11. So these are the weights. So weight can be any kind. So various applications are there. For example, in case of, if we consider the vertices are the name of the cities, and the edges are the roads that are connected to these cities. So we will consider these weights as the distance between two cities. For example, in case of network flow analysis, if you consider the the nodes are the switching modes or switching points, and the edges represents the flow of control from one node to another, so we can consider it is a unit of the flow from one node to another. So the problem is, what will be the minimum spanning tree for the graph G shown in figure 3. So we will, before going to solve this problem, we will discuss about the difference between the minimum spanning tree and the shortest path. So in case of minimum spanning tree, we can solve this minimum spanning tree on the undirected graph, whereas shortest path can be solved on directed as well as undirected. Any vertex can be selected at start in the minimum spanning tree, but in case of the shortest path problem, the source and the destinations vertex are given priori, and we have to find out the shortest path among the source node as well as the destination node. In minimum spanning tree, sum of weights of spanning tree is to be minimum. In case of shortest path, the sum of the weights from source to destination is minimum. Minimum spanning tree is having algorithms such as Prim's algorithm and Kruskal algorithm. In similar manner, shortest path problem is also having solutions from Dijkstra algorithm. So we will go with the problem that we have discussed earlier. Before proceeding to that one, we will discuss the historical background of the minimum spanning tree. So this problem has become very popular after the World War. Various So in 1925, an employee of Western Moravian Power Plant Company asked Borovka to solve the following task. The task definition is: design the cheapest electrical network connecting all the given towns in Western Moravia. Basically, it was asked to find the minimum spanning tree for this area. So the problem definition that is being created by the Borovka is includes input a matrix of n cross n of positive integers and zeros on the main diagonal is given. The number in the matrix represents the weight on the edge, and the task is, from each row or column one number must be chosen. The sum of these n minus 1 numbers should be minimum of all such sets. So Borovka has proposed one algorithm for finding the minimum spanning tree from the matrix. Borovka has solved the problem without without considering the concept of graph. So he had given the solution on the basis on matrix only. So the algorithm of the Borovka is having the following steps: choose any row in the matrix. So as we have already stated that in the minimum spanning tree problem, we can select any of the edge at start. So we are selecting any row in the matrix, then choose the smallest positive number in this row. This means that two vertices, the row index and the column index, have been chosen together with the edge between them. Consider this as a T1. So this is the first partial minimum spanning tree. Then algorithm is now divides two branches. Is there a number in new row determined by the column index from step 2 that is smaller than the number included in the minimum spanning tree in the previous step? If yes, the smallest of such numbers becomes a new member of the minimum spanning tree. Then perform step 2 and step 3 with newly added number. If no, choose a different row and perform the step 2 and step 3. The algorithm proceeds until there are no isolated rows. This means that a maximum number of repetitions is n minus 1. Then we get several partial spanning trees which need to be connected. Compute a new distance matrix for partial spanning trees. Go to step 1 and perform the algorithm for the new matrix. And the output we'll get after execution of this algorithm is a sequence of vertices determining the minimum spanning tree. So now it's time we'll go for the example that we have shown in the figure 3. So the figure 3 graph is shown on the slide, and the weights that are assigned on the edges are also shown in the matrix of 10 cross 10, as we have stated that there are 10 vertices and 21 edges. So a matrix of 10 cross 10 is created. Now the first step of the Boruca algorithm was to take any row at start. So for example, we will select the row of G, and the second step is to select the minimum value from this particular row. So we are selecting the minimum value from this row is 8, so which is G to J. So we have already selected one edge. Now at second we will go for the J row. We will check for the minimum value here also. So here the box green box is showing that we have already selected this particular value earlier, while the yellow box is showing that we are selecting the minimum value at this time. So now we have selected 2 as the minimum value among these two rows, the row G and the row J, from which we have selected the 2 as a minimum value, that is from J to I. So now we will get another row of I. So now we are having 3 rows. So among these 3 rows, whichever will be the minimum value that we are going to select. So from these 3 rows, you can easily see that 7 is the minimum value, 3 is the minimum value, and then we will get the H row. From that we will select 5 as the minimum value. Then we'll go for the D row. Then we'll select 1 as the minimum value. Then we'll go for the E row, and we will select 6 as the minimum value, that is from E to B. So we will get now the B row. So now from B row, among all these rows that we have already selected, we are getting that B to C is the 4, and that is the minimum value. So we have to select that one. So now we have selected 4. Now once again we will go for the C row, where we can see that the values that we are having are maximum as compared to the previous rows. So we will go for the F row. Now what is happening here is we are selecting that particular value which is being connected by the another vertex. So in the C row we are having the values greater than 7. So next value that is to be selected is ultimately the 7th one, that is not to be available here, but the vertexes that we have already selected is connected to F node, F vertex. So for that purpose we have to select this particular row F, and the value that is to be selected is 7. Similar manner, at last we have to select the A row, and the value that is to be selected is 9. So now finally we got our minimum spanning tree weights. So we can easily see that all the weights starting from 1 to 9 are being selected, and we will get the final minimum spanning tree. So in the slide shown, this is the resultant minimum spanning tree. So you can compare with the matrix that we have created earlier. So we can see that all the edges that are having the weights starting from 1 to 9 are being get selected. So now we'll discuss about the other approaches that are uh, used for finding the minimum spanning tree. For example, Prim's algorithm and Kruskal algorithm. So Prim's algorithm, it is being found that the Prim's algorithm is same as the Borovka's algorithm, and the Kruskal algorithm, while constructing the minimum spanning tree, every time it selects the edge which has the minimum weight and adds that edge if it doesn't create a cycle. So in Kruskal algorithm, we are selecting the edges that are having the minimum weight, and we are just checking for the condition whether that particular edge creates a cycle or not. And it has been found that all the algorithms will produce an unique minimum spanning tree. Various applications of minimum spanning tree are, while designing the computer networks, we can use the minimum spanning tree concept. For circuit design, we can use the minimum spanning tree concept. For cluster analysis, we can use the minimum spanning tree, and for electrical grid also we can use the minimum spanning tree. So various other applications are also available for minimum spanning tree. So now it's a time to take an exercise. So find the minimum spanning tree for K5 with weights given in the matrix in table 2. So K5 is a complete 5 graph which is having 5 vertices A, B, C, D, E, and the edges are given with their corresponding bets assigned to them. So from this we have to find out the minimum spanning tree. So this example is taken from the CZ Digital Mathematics Library, and this was the actual problem that was given to the Borovka to find out the minimum spanning tree among these 5 cities that are connected to the Moravian power plant. So the solution of this will be shown in the slide, as we have to select the edges A to E, C to B, D to A, D to B, and F to C. These are the references that I have used for this lecture. So I have used the papers that are presented in the various conferences and the journals. Thank you.